bivariate data analysis. So we mentioned this word in the beginning of the unit, okay? We picked it apart and we said bi means two and variate means variable. So this is dealing with two variables. And it says statistical studies are done where data is collected on two variables instead of one, so that we can see relationships between the two. This is called bivariate data analysis. So we're not just cranking out numbers, we're taking those numbers, we're looking at it, we're analyzing to make some interpretations from there. So the survey was taken of 10 low temperatures, 10 low and high temperatures in Fahrenheit in the month of April. So 10 days they recorded the high and the low temperatures in April to try to establish some kind of relationship between a day's low temperature and a high temperature. So you know when you look at the weather, it gives you the high and the low temperature predicted, okay, for a particular day. So they listed them out in our table where the low temperatures are the X's and high temperatures are the Y's. They want us to construct a scatter plot on the grid. Then we're going to draw the line of best fit. Then we're going to calculate slope. So I'm going to pause and let's go ahead and do that scatter plot. We'll come back to the line of best fit. Okay, so your scatter plot should look like mine, applying those 10 points. Now it says draw the line of best fit through the data. So a line of best fit is just that, okay? Yours might look slightly different than mine, but you're putting a line in there that best represents this data. You try to have an equal amount of points above the line as you would below the line. You try to get it kind of right in the middle of the points. When we look at the points right now, we can look at that it's kind of got that upward trend. It's kind of got a positive slope to it. So that's exactly what our line of best fit is going to look like. So use a straight edge of some sort and draw in your line of best fit. And it may or may not touch any data points that you plotted. Okay, it may or may not. Okay, so there's my line of best fit. Like I said, it may or may not go through data points that you plotted. So once we've drawn that line in, now it says, part C, calculate the slope of the line by picking off 2 points, not necessarily data points. So I want to pick 2 points off of the line. So the line that I drew in, I'm going to pick, let's see, this one right there looks pretty good. And then, I don't know, that one looks pretty good right up there. Okay. So pick 2 points off of your line that are nice points that you could figure out what they are pretty easily. So my 2 points, I'm going to use 30, 54. And my other point, which is 44, 46, 72. Those two look good. So now my slope formula is change in y over change in x, or y2 minus y1 over x2 minus x1. So now take your 2 points, calculate your slope. And I'm going to calculate my slope, and we're going to see that they're going to be really close. Okay? So go ahead, do the calculation of your slope while I do the calculation of mine. I'm going to take and simplify mine so we end up with 9/8. Mine does. A little over 1. Okay. Is your calculation, your slope, close to mine? Okay. A little over 1, a little under 1. somewhere within the range or close to 1. Okay? All right? And that's what it's supposed to be. Positive, okay, pretty close to 1. Now it says, using your line of best fit. So the line that you just drew in to estimate the high temperature for a day in April, given that the low temperature was 42 degrees. So if we go to the low temperature of 42 degrees, go ahead and meet your line, and what do you get? I get, what do I get? 62? I get 68, roughly, 67-ish, okay, 67, 68-ish, okay, roughly 67 degrees Fahrenheit is yours close to mine, okay, somewhere within that range. Now it says, would you characterize the relationship between the low and the high temperature as a positive correlation or a negative correlation? Meaning, as one goes up, the other goes up, or negative correlation, as one goes up, the other goes down. Thinking about high and low temperatures, looking at the graph, thinking about your background knowledge of high and low temperatures for a day, is it positive or negative? It's positive, right? And then it says explain. So positive because as low temperatures go up, high temperatures go up. Right? Or if we talk about in terms of the parameters of our line, we see that the slope is positive. Therefore, it's a positive correlation. All right, go ahead and flip the page. Then it says two variables can have a strong relationship with one another, as seen in the seen on a scatter plot, but might not have a. Look at that word closely before you say it in your head. Okay, it's causal relationship, not casual. Okay, casual is spelled differently. Okay, a causal relationship. A causal relationship exists when the change in one variable actually causes the change in the other, or is one of the primary causes. One causes the other to happen. So it says, in each of the following scenarios, two variables are given that, if plotted, would have a strong correlation. We already know they are correlated. Okay? A scatter plot where the data falls nearly in a line. Okay? We know that they are strongly correlated or related to each other. Determine now if there exists a causal relationship. Does one cause the other to happen? If so, which variable causes the other? So we've got 4 examples here. So let's do this first one together. The height, or excuse me, the high temperature in New York City and the number of bottles of water sold. Does one cause the other to happen? Okay, you're saying, you guys are shaking your heads, you're saying yes. Okay, so does one cause the other to happen? Why? Yeah, what do you think? Yeah, okay, the hotter it gets, okay, the more people are going to get thirsty, the more we're going to sell those bottles of water. Okay, so the high temperature is going to cause the sale of bottled water to go up. Temperature causes bottled water sales to go up. Okay. All right, I'm going to pause it. I want you guys to B, C, and D, and then once you've done them, come back and check your answers. Okay, a person's height and a person's shoe size. Does one cause the other to happen? Yes. Does one cause the other to happen? We know that they are correlated. Okay, we know that there's a strong positive correlation. That as the taller people get, okay, generally they have bigger feet. Right? But is the person's height causing their feet to grow? No. No. Okay. said, they're correlated, definitely. But it's one is not causing the other to happen. A person's weight loss is the number of hours a person spends in the gym per week. Does one cause the other to happen? Maybe.
The number of hours a person spends in the gym causes weight loss.
Yeah, okay. Yes. As gym time increases, okay, that weight loss increases. That talks, yes, that kind of addresses our correlation piece. And one is definitely causing the other to happen. So the gym time is causing the weight loss. Okay. Last one, the years of education a person achieves and the salary that a person starts at upon entering the workforce. Does one cause the other to happen?
Yes.
The number of years you spend in college, does that cause your salary to increase? Yes, it does. Okay. Yes, it absolutely does. Okay. Think about that doctor that spends time. Okay, we're talking in general. Don't try to think about the exception to the rule. Okay. The doctor that spends 7, 8 years in school, okay, what are they going to come out with as a starting salary? They're definitely going to come out with more than somebody that spent maybe 2 years in college. Okay? Or I'm not, like I said, I'm not addressing the exceptions to the rule. Somebody that doesn't go to college at all, but maybe walks into a family established, successful business. Okay, their starting salary may be pretty good because that business is already established. So we're talking about that in general, yes. Your time in college, okay, or years of education cause your starting salary to increase. Variables can have extremely strong correlations, but no causal relationship. There is often the case, if this is often the case, if there is a third variable that causes both, and it's called the lurking variable. Okay, so you've got two variables. There's definitely a correlation between the two, but one is not causing the other to happen. But there's a third variable that kind of sneaks into the mix that causes the other to happen. So let's look at this data. It says, the table below shows the number of firefighters required to fight a given fire versus the dollar damage done to the house by the fire. Okay? So the damage done to the house by the fire and the number of firefighters. So we've got, you can kind of scan this data and see what happens with the number of firefighters as they go up, what happens to the damage done in dollars by the fire. Are the data positively or negatively correlated, and how can you tell? Bobby?
Positive, because like as the numbers go, like as like your firefighters go up, like the damage goes up.
Yep. Yep. So as the number of firefighters goes up, see that from the table, the dollar damage also goes up. Okay? So it's that positive slope. It says, does the number, now think about this one, does the number of firefighters, Maggie, do you have an answer or a question? Okay. Does the number of firefighters cause the damage done to the house? If not, what hidden variable is causing both variables to change? Does the number of firefighters cause the damage done by the fire? Or is there something else? Maggie? Yes, is the lurking variable. Okay, that size of the fire is, the bigger the fire, that's going to bring in more firefighters, and then that size of the fire is going to do more damage. Okay, so that money is going to increase. So that third variable, okay, or that lurking variable is the intensity or size of the fire.